Okay, well, welcome back. So we've had a panel on the mathematical and algorithmic foundations of computational science and engineering. We had another panel on the specific challenges and opportunities in computational medicine. And that brings us to the third and final panel. This one is broader and essentially targets impacts in computational science and engineering in several different areas. The panelists are doing exemplary work in their individual fields, and you'll see some of that. I'm going to give the briefest of introductions and ask the panelists to tell us about their work. So I'll start with Stella Offner. She's an associate professor in the Department of Astronomy. She is a core member of the Institute and of the Center for Scientific Machine Learning in the Institute. Her research is on trying to understand the fundamental nature of star formation in stars such as the sun. Patrick Heimbach is Moncrief Chair and a professor in the Department of Earth and Planetary Sciences. He leads the computational hydraulics. No. That's Clint.
Since when?
He's adjacent to the. No, he leads the CRIOS group, which is the Center for Research in Ice Ocean Systems. And he is, well, as you can tell from the name of his center, his research focuses on an understanding of general circulation of the oceans and their impact on the climate. And then finally, Clint is the newly appointed chairholder of the Cockrell Chair in Engineering. He is a professor and chair of the Department of Aerospace Engineering and Engineering Mechanics. And he leads the computational hydraulics group in the Institute, and his research is on flow and transport in porous media and in shallow water systems. So what I'm going to do is really I have just two broad classes of questions. The first is a retrospective look at the careers of the panelists at the Oden Institute. What has the Oden Institute meant for them? Stella is one of our newest, in fact, maybe the newest member of the Institute. So she'll have less to say on that. Patrick is well, we'll go to the other side of Clint has been here, probably one of the longest members in 28 years. And Patrick is somewhere in between, closer maybe to Stella. So they'll share their perspectives. And so the question is, what has being in the Oden Institute meant to you and your research? So we'll start with Stella.
All right. Hello, everyone. Yeah, so I've been maybe affiliated with the Oden Institute for 2 years and core faculty for 5 months. So this is more of what the Institute can do for me and what I can do for the Institute in the future. So let me tell you a little bit about my research. So I am at trade a computational astrophysicist. So I do large-scale simulations of how stars form. To translation is I do a lot of fluid dynamics. I solve a lot of PDEs. I do high-performance computing. TAC is one of the main reasons why I came to UT, because it's phenomenal. I use it and log in every day, as do most of my students, so it's fantastic. So the other side of my research is in scientific machine learning, which is a newer passion of mine. And so I work on both kind of supervised neural network type applications and also unsupervised clustering, dimensionality reduction. What I'm fundamentally trying to do with that work is to connect simulations, which make beautiful training sets, beautiful labeled training sets, with observational data, which are messy and very confusing and complex and noisy. And so I think this framework of using simulations has been really incredibly important for learning to understand the universe around us as we observe it with a wide variety of telescopes, most recently JWST, the James Webb Space Telescope. So Oden. So I view Oden as a nexus point of real intellectual activity. Since I work on PDEs, there's been a very strong focus of the Institute, and it's really phenomenal to be part of this where I can go and talk to experts on how to most efficiently solve systems, how to optimize systems. I'm part of the scientific machine learning group, and so just having that interaction is very important. What I have learned is that machine learning, it's algorithms. You provide the initial conditions, which means that the algorithms that I use in my techniques are also being used in climate modeling. They're being used in geosystems. They are used in all kinds of medicine. And so this institute has provided a really great place for conversations, for collaborations, and I'm hoping to continue to build a lot of connections going forward with people in the institute.
Great. Thank you. Patrick?
Yeah, thanks, Omar. I was sort of semi-encouraged to show slides, and so I use that to sort of set the stage a bit like the double bass player in an orchestra who tries to justify why he's important in the orchestra. So here we are trying to, why is the ocean important in the climate system? And in fact, it is important. It takes up more than 90% of the Earth energy imbalance, so the extra heat that comes into the Earth actually ends up in the ocean. We have about almost 30% of the CO2 gets absorbed by the ocean, and then of course all of sea level, the fresh water that gets in basically rises sea level. We're in the midst of the UN Ocean Decade of Sustainable Development, so a huge interest in trying to understand sort of this vast reservoir better for sustainable development, food security, and so on. And we had the IPCC report that focused on the ocean and the cryosphere with the understanding that there are massive changes going on in the polar regions. And so with the advent of all of these satellite data that we have that are ocean dedicated, we are having a lot of data, but the question is ocean science or is it a big data science? And from one perspective, actually from a simulation perspective, whoops, sorry, that was too quick. So that happens when you face backwards. So we are able actually, again, with TAC resources, so since I'm here, we've been able to conduct these permitting eddy resolving simulations of Arctic Ocean circulation. They create huge amounts of data, so per simulation on the order between 10 and 100 terabytes of data, and there's other climate model simulations that produce even more data, and so really we are able to, solving the governing equations of motion to really improve our understanding of how the climate system in these polar regions are changing here. My colleague Anne Nguyen, also here, senior research scientist in my group. But the question is, so the models are powerful tools, but there's some fundamental problems, like with other large-scale applications. They're very expensive to run. And in fact, if you see on the slide, you see the succession of what are called IPCC generations that have been this Intergovernmental Panel Assessment since the 1990s up to today, and the improvement in resolution has just not been able to keep up with the computational hardware capability. So really, climate modeling is increasingly lacking behind the actual capabilities that potential hardware would render itself. The other question is, and it was shown this morning, the question is of how do we actually quantify uncertainties in these uncertain models? How do we calibrate these models? And that's actually been under-addressed, I would argue, in the climate modeling community from a rigorous perspective. How do you confront those models with data to do proper model calibration and initialization? And so then we ask the question again, are we a big data science? We're producing a lot of simulated data, but observationally, we're actually an extremely sparse data science. It's very hard to observe the ocean, especially in the interior. So we have these two incomplete knowledge reservoirs, sort of very sparse observational data and imperfect and uncertain models. And so how do we bring those two model reservoirs together? And that's basically a problem of sort of Bayesian inverse methods. That's something that we have actually been able to do within a NASA-funded project where we actually bring together these very disparate, heterogeneous, sparse observation with models to bring the best of both worlds. And since my arrival here at the Oden Institute, I've actually been here to actually learn a lot from my fellow faculty. For example, from Omar, how do you do rigorous uncertainty quantification? And how do you use these models to design observing systems, understanding that it's extremely costly to go out to sea with a $20,000 per day ship time to basically operate, to put out moorings. So in these situations, you really want to basically have models guide, what's the best bang for your buck, how and what type of observations do you place where. So this combination of basically improving model calibration in this context of Bayesian inference inversion, beginning to produce sort of rigorous uncertainty quantification in the models, in the calibration, and in the observing system design are sort of efforts that have been started here. And so maybe with this I'll stop and leave it.
Okay, thank you, Patrick. So Clint, tell us a little bit about yourself and what it's been like to be here.
Right, so I came here in 1995 from Rice University, where I was in the Computational and Applied Math department, which was basically the numerical methods for PDEs part and a operations research part. And there were three of us, Todd Arbogast, Mary Wheeler, and myself, who came here from Rice all together as a group. We brought all of our students and postdocs with us, so we came with about 12 or 13 people, and basically moved the whole group to Austin. At that time, the institute was much smaller. It was in a building that was on this footprint, an older building that had been renovated called Taylor Hall. And there were, I don't remember, maybe 10 faculty at that time, around that many, and probably 20 grad students and maybe a few postdocs and then visitors going in and out. So it was a much different feel. It was a much smaller institute, so we were very close knit. Ate lunch together every day, so it was just a different, as opposed to this, which is amazing. So if you look at this, you see the impact of the institute. In terms of my own research, I came from Rice and I was in a math department, applied math department. I went into engineering, that was a big shock in the sense that I was not a trained engineer, especially not an aerospace engineer. I went into sort of the engineering mechanics side of the department, I guess, which, I hate to say there's a side, but I was in the computational mechanics group along with Tinsley Oden and Ivo Babushka and Mary Wheeler and Graham Carey and Linda Hayes and Eric Becker and Leszek. And Leszek was there. So there were, I was doing finite element analysis, primarily for flow and transport and porous media at that time when I came here. And there were sort of three things or so that really were invigorating about being at the Oden Institute at that time and are still invigorating today. One was it was a hotbed of finite element methods. It wasn't just three of us working on finite element methods. It was a whole bunch of people, and it was sort of a competitive atmosphere. We all pushed our methods, and we sort of drove each other. And it was great because one idea would feed off another, and then our students. We were able to train a lot of students. Beatrice was one of the students that was here at that time, and so that was very invigorating. A posteriori error analysis, I had never really been exposed to that, but that was a big thing in the engineering finite element community, especially in Tinsley's group. And then uncertainty quantification, that came along a little bit later, especially when Omar arrived, and so that had a big impact on my research. Is just the idea now that we need to really measure uncertainty, and then the idea of verification and validation, which we had done, of course, like convergence analysis of our algorithms, and we showed that they converge with the right rate, and we could match analytic solutions, but then if you're going to solve really difficult engineering problems, then the whole idea of verification and validation gets to be a lot thornier. So those three things really exposed me to algorithmic ideas that I hadn't really grown into as a professor at Rice. All that's carried on over the years. Now, of course, it's machine learning, and other aspects of data science that have become integrated into our research. The other thing that really changed, well, another thing that changed the direction of my research was I started getting more into coastal ocean modeling because of a collaboration that I had with some people outside of UT. And that was around the time in the late 90s, early 2000s, when there were starting to be more and more hurricanes, more and more destructive hurricanes. And there weren't good models to simulate the storm surge that resulted from the hurricane. And as commented earlier by Michael Sachs, even the hurricanes themselves were poorly represented in physics-based models. So we started working on developing a high-resolution model of New Orleans in the late 90s and early 2000s. And then all those hurricanes happened in the 2000s, Ivan, Katrina, Gustav, Frida, Ike, et cetera, et cetera. And that set me on a path that has led to sort of where I am today, which is really embedded in the coastal ocean modeling community. Hand in hand with that was the evolution of TAC. When I first came here, TAC was still a Cray vector machine dominated outfit. It was sort of running on fumes, I would say, at that point. Then Dan and Jay Bosso came in and completely transformed, along with the help of the Oden Institute and the O'Donnell Foundation and Tinsley and a number of people. Larry Faulkner got behind it. And actually, that probably, more than just about anything, changed the direct trajectory of my career, because nobody has resources like we do here, and we couldn't do the work that we do without those resources. So I don't know, for all of you students out there, I don't know how lucky you are. I don't know if you realize how lucky you are to have that resource available to you. So those were the things that were really impactful. The other thing was the evolution of the CSEM program, the ability to recruit fantastic grad students, to offer them fantastic fellowships, to be able to recruit postdocs into this wonderful facility. When we moved into this facility in 2000, that was a life changer, a game changer. We've been very lucky to have great facilities. Being in Austin for me, that was important because it gave me access to the state agencies that I work with today. The Texas Division of Emergency Management is located here. I would not have had necessarily those same connections if I was still in Houston. And then just in general, the reputation of UT, the reputation of the Oden of TICAM and then ISIS brought in a lot of visitors from outside. We have this wonderful visitors program. There were always people coming through. If we wanted to invite someone to come, it was easy to do that. They could stay for 2 weeks. And that had a huge impact on my research as well. So those are just some of the things that I can think of.
Okay, thank you, Clint. I have to say, when Karen showed the picture of Todd and you and Mary when you moved here in 95-ish, you haven't changed much from that picture. So
no.
whatever you're drinking, I want some of that.
I don't agree with that.
Anyway, thanks for marching us through the years and from your personal perspective and bringing us to today. So that leads to the next meta question, which is, how do you see the future in your particular field? How do you, what are the exciting things? What animates you? And where do you see things going? And, well, let's cycle back and start with Stella again.
All right.
So again,
Stella
Stella
has... We'll have to go
has...
through all of your slides. See a beautiful movie again to get to my slides, which are there. There we go. All right. I don't know if there's a rule that I have to remain seated, so I'm not going to do that because I can't see that. Yeah, you can't see behind you. So I'm addressing the frontiers in astrophysics. I know there's maybe only a handful of people in here who are bona fide astronomers, so I thought I would do this best if I could give you a visual tour of what's happening. So the first advancement, which I think we're going to get to over the next decade, is end-to-end modeling of the universe. So here's a beautiful schematic of how we think the universe evolved from the Big Bang to the present day. Now, what we currently do is we pick out certain subregions and subtimes of the universe, and we model them. We model cosmology, we model galaxy formation, we model star formation. And so I have a few examples of these kind of simulations. Cosmology typically starts from the early perturbations of the universe. The initial conditions are relatively simple. You're following the evolution of dark matter, often using particle-type codes. And you can follow for a long period of time, and eventually you see how the structure of the universe evolves. Now, those are not so great at modeling galaxy, individual galaxy formation calculations. So to date, what we do is we pick out some initial conditions, maybe more artificial, and then we model the formation of what we think a galaxy like the Milky Way, how it would have evolved and interacted with its neighboring galaxies. Now, again, that is not able to get down to stars and planets. So what we do again is we pick out some more simplified initial conditions, and we follow the evolution of that gas down to the formation of individual stars, and this is also happening for planets. You can already see that in all of these areas is very, there's a lot of fluid dynamics in there, compressible MHD turbulence. We have a lot of physics. And this one on the bottom right, you're seeing a cluster of stars forming, including a variety of feedback, outflows, jets, winds. Eventually, if we watch it long enough, there'll be a supernovae. But what's actually going to be going on in the next 10 years is we're going to begin to start connecting these different epochs of the universe. And one way we're going to be doing that is through zoom in or adaptive resolution calculations, where we can run our dark matter simulation. We can populate it with baryons to a certain extent. Once we have galaxy formation, we can take out a galaxy and zoom in onto the scales and time resolution that we need to do stars, and continue on until we get to planets. And so what you're seeing here is a paper in PrEP, which is modeling the formation of a galaxy starting from large-scale structure and zooming in down to the inner disk around the accreting black hole. So we're talking about 8 orders of magnitude in spatial scale, 10 to the 18 orders of magnitude in density. And so this is what we're going to be able to do in the next decade, and it's going to be so exciting. The next thing is learning the universe with AI, just like what everyone else has been talking about. There's been a revolution in astronomy of trying to learn and apply these different machine learning techniques. This one on the left is from my group, using a 3D convolutional neural network. We were inspired by this actually from medicine, where we saw a paper maybe 6 years ago where they were using labeled training data to identify tumors in MRI scans. It turns out that works really well for identifying stellar winds and feedback features in observational data. And one of the key advancements is the bar is so low. So before this was being done by eye, that was the state of the art. We have humans going through the training sets, going through the observational data sets, and picking out by eye where the feedback is. So many problems with that, right? So many problems. So now we're automating this. This paper on the right is the first large language model tuned to astronomy data, which was put out last week. So we are really embracing the whole AI revolution, and I think this is really going to push science forward. Automated feature detection. I haven't heard much about this now, but I think we can accelerate PDE solvers with AI neural networks. And of course, we can build the AI astronomer who will help us understand and search through the literature, understand and discover things in the data. Last thing, astronomy has entered an era of big data. We always said, I'm sure in astronomy, every 10 years we said, okay, this is the era of big data. But no, I'm serious this time. This is the era of big data. Right, so just to name a few, we have ongoing survey of Gaia, which is a space-based mission. They've been surveying 1 billion stars in the galaxy and nearby galaxies, looking at them multiple times, unprecedented resolution. For the first time, we can pinpoint stars in 3-dimensional space, and you have no idea how hard that is. The next thing is we've had these ongoing surveys of dark energy. So this is 3 petabytes of data. It's a large optical survey surveying the night sky, looking at hundreds of millions of galaxies and trying to understand the formation of structure over time in the universe. Last but not least, coming next year is the Rubin Observatory. This is going to generate 3 petabytes of data each year. It's going to be surveying the night sky, multiple times. What is it? Every few nights they do the entire night sky. It's incredible. So this is going to revolutionize our view of the universe in the time domain. We're going to be seeing these supernova events, doing follow-up, real-time, online data processing. And so right now, astronomy is not ready for this, but that's what we're doing right now. We're getting prepared for it. And so there's a lot of areas where astronomers are collaborating with experts in AI and trying to move some of this application forward so that we are prepared. So those are my 3 main things we're going to do in the next decade.
Okay, thank you, Stella. Very exciting. That end-to-end, universe simulation, is that referred to as the initial value problem?
It is the initial value problem.
The mother of all
Yes.
initial value problems. Yeah. Okay, Patrick, do you want to weigh in on the future in your field as you see it?
Yeah, it's actually an exciting time. It's just over the last maybe even 2-3 years, there's sort of 2 or maybe 2.5 sort of trains of thought in the community of where climate modeling in particular, and which of course includes ocean modeling, should go. The one is really to resolve the heck out of the system, right? So we are basically, or people are trying to do simulations at the kilometer scale resolution in the atmosphere. Kilometer, the reason for that is basically you're resolving sort of convective cloud systems. In the ocean, incidentally, at the 1 kilometer, you would not only resolve what we call the mesoscale eddy field, but also what's called the submesoscale, so certain ageostrophic motions that will impact the mesoscale, and therefore, again, sort of where you go down to the 1 kilometer resolution, you have a coupled system, and then the notion is that many of the climate model simulations that we have right now are parameterizing all of these processes. And for decades, basically, these climate models have been beset with the same types of biases, and they've basically really been very little progress in trying to improve, even the parameterization schemes or the radiation schemes. There has been very little improvement, and so basically the idea is now, let's resolve the heck out of the system. And the problem here is, and in fact, some people, there is a concept of the digital twin of the Earth that basically frames it that way, but what that picture is not, so that digital twin is actually not learning from the data, right? So because these simulations are so expensive, so there's been one at the ocean side only, it's a few years ago already, but it's the highest, probably the highest global simulation that's been performed on the NASA Ames Pleiades machine. That's already a few years ago. But the throughput has been 0.04 simulated years per day, right? And so if you remember from this morning, climate modeling, we're somewhere we would like to have at least 5, if not 10 simulated years per day, so that we can actually run centennial simulations, and we can run ensembles of these simulations to begin to span in some ways the uncertainty space, even in a crude manner. So the other problem there is also that the idea that you basically just things are falling into place at 1 kilometer, just that doesn't work, right? So there is a turbulence cascade that basically goes down well below the 1 kilometer scale. There are certain features in the atmosphere, for example, thin low cloud cover that are on the order of 50 meters that you actually are not resolving. Very important for deviation balance. In the ocean, you have the ice-ocean interaction problem where you begin to look at how the ocean in contact with the polar ice sheet at small scale, at the 100-meter scale, at grounding lines of ice sheets basically are impacting sort of potentially increased ice mass drainage from the ocean to from the ice to the ocean. So the notion that it will just fall in place without any proper calibration, bringing in the data, trying to constrain the system with the observations is not there on that side. And so there's the other school of thought that actually says, no, we have to be able to still run at a resolution where we can afford longer-term simulations. At the same time, we have to bring in methods that are inverse methods, or some maybe methods from machine learning, but especially inverse methods, to actually use the data that we have to actually properly calibrate the models, to calibrate the parameters that we have. This is completely underutilized or non-utilized in the climate modeling community. The CMIP efforts run coupled simulation forward, and the tuning of models are, they're not methods, but they're names. They're highly respected experts at the supercomputing, at the modeling centers who know which knobs to turn, but that is no longer sufficient to actually develop well-calibrated models. And so the other school of thought is, let's stay at a resolution that we can afford running larger ensembles, but then let's bring in inverse methods or machine learning methods on how we calibrate models, and potentially this calibration could be to replacing some of these uncertain parameterization scheme with subgrid models that can both accelerate the model performance itself, but then also can really be calibrated to actual either observational data or to simulated data that come from very regional LES simulations. So that also brings in the notion not of just a much better calibrated models, but also of basically doing uncertainty quantification and then looking at other methods. There's a number of approaches. There's smoother-based methods like a Kalman smoothing methods. The one that we're advocating is what's now sort of become popular in the age of machine learning, sort of the notion of differentiable programming, but that we used to call adjoints, right? But that's basically the same thing that we do online full model learning, where we basically bring in the entire, so we train and we constrain with using inverse methods these model simulations using these kind of methods. That requires close collaboration with the computer science people who develop, for example, new tools of advanced general purpose automatic differentiation tool. Again, something that's become very fashionable in the age of machine learning. Oh yeah, of course, automatic differentiation, but that's been known in the simulation-based science for decades more. And so these are two competing fields. I should say that there's advocates that say we need to develop like a CERN for climate modeling to be able to put all the resources into doing these very high resolution simulations. And that has very strong appeal, but it also is still lacking this. How do we bring in the observational data? How do we parameterize what still needs to be parameterized? So these two schools of thoughts, then I should mention, the advent, there's sort of the notion of hard AI versus soft AI. The soft AI is what I kind of described previously, that we try to bring in judiciously, kind of machine learning for a regression type of surrogate modeling where we replace uncertain and very expensive parameterization or physics schemes for cloud parameterization or eddy parameterization, and we replace them with well-trained surrogate models that can be neural networks or the other types of models. And that's kind of in our community considered as a soft AI, and then the hard AI would be the one we can completely replace the forecast models, the physics-based models, and do forecasts with well-trained neural networks. And there has been some stunning successes on the weather prediction side. So there was at least over the last year, at least 4 groups at different centers at Microsoft, Google have brought out papers where they basically say they can keep up or beat 10-day forecasts of the ECMWF, the European model, to some extent. But it should be pointed out, two potentially limiting things is these models, these networks have been trained on model data. There is no observational data on which to train the model, and these are model calculations of which we are, actually not very proud of, right? So then if we want to improve the training data, the main emphasis should still be on the algorithmic changes to improve the physics-based models, right? So that we have better, even if we wanted to have better training data, which we of course could do regionally with LES simulations, but just to point out that one caveat. The other is that there's a notion in the community that this works well for shortwave, so for basically weather and potentially subseasonal to seasonal forecasting. But then once we go out to climate timescales where we have a very noisy system and we're trying to basically detect climate signals that are sort of small residual in the noise, conservation laws, we play an important role over these long timescales. I think there's a consensus in large parts of the community that the simulation, the physical simulations will be indispensable to do these climate simulations. You will not be able to do hard AI on climate applications that are longer term, that go beyond, let's say, the seasonal timescale. Maybe 10 years ago, I'll sit here and will be proven wrong, but that's sort of my prediction for today.
Thank you, Patrick. Lots of great opportunities and challenges also. So, Clint?
Okay. So one thing is for us is integration across scales and physics. And I know we've all been talking about multiphysics for a long time, but it's still an unsolved problem in my view because we can couple maybe 2 or 3 processes together, but what we really should be doing is bring in atmosphere, ocean, coastal to inland, inland to rivers and channels. And these are all coupled both ways. Then land surface to the subsurface. And then in our situation, all of that has to interact with structures, with development, and that complicates very complicated coastlines, so that complicates our calculations quite a bit. We have typically very rough geometry. I'm a big fan of resolution. We're still, whether that's actually mesh resolution or running at higher order, it could be a combination of both. I still think that resolution is a key to getting accurate results. But that also comes at a cost, and we're finding more and more that we need to be running multiple ensembles of calculations, both in real time and also in doing more long-term studies. And that's also true when we're doing uncertainty quantification or parameter estimation. Parameter estimation across physics is still not well understood, like how does one process, how do missing parameters in one process affect all the other processes that process is coupled to. That's another thing for us where machine learning, I think, has some promise, and besides just as a predictive tool, but maybe to help us perhaps calculate faster ensembles or train an ensemble calculation to do more things. I do think a big challenge for us is going to be transforming our algorithms to GPUs, although maybe after the talk this morning I'm less worried about it because it sounds like something's just going to magically do that for us. But at least it looks rather daunting to take a code that you've been working on for 30 years that has all these bells and whistles in it and all these different kinds of algorithms and data and get it translated into a GPU, especially the input and output and we're dealing with multiple millions of degrees of freedom. In my world, we've had a data explosion in the last 20 years where we started out with just a few gauge measurements at various places in the ocean, but now we have 10 times more gauge measurements. We have satellite imagery. We have pictures from cell phones. We have, LiDAR, INSAR. LiDAR data is now down to below the meter scale, so we can actually get like land surface roughness and bathymetry at scales that we don't even know how to deal with, whereas years ago we didn't have that. So there's been a huge data explosion, which has its pluses and minuses. So the area that I work in operates at both a real-time mode and at a sort of the mode where we try to understand things that happened in the past, or we try to make predictions of what might happen in the future. But forecasting is really tough. It's really living on the edge, and you have to, I don't envy people that have to do forecasts for a living because your codes have to run, they can't blow up, you have to produce an answer. And there's some trade-offs to be had there, but I think there's actually some research to be done around how to do effective forecasting that isn't just necessarily in the domain of the operational agencies. Another thing is how we deal with climate change in our models. I mean, we do deal mostly with short-term events, but climate change affects those short-term events over long time scales. So right now, we don't really have very effective ways to deal with rising sea levels, the melting ice sheets, changes in wind profiles. I mean, I think this year we've seen more strange weather events than I've ever noticed that have, kind of shaken us to the core about the impacts of climate change. Yeah, so I deal with a lot of missional agencies, NOAA, Army Corps of Engineers, Texas Water Development Board, and they have operational needs, right? So they have to run operational codes, but so this transition of research to operations, I think, is a challenge. I think they want to accelerate that, but then they also have to satisfy the public and their stakeholders and Congress, and they have to be good stewards of the information that they provide to the public, because they are the Weather Service is the face to the public, right? So they have to provide good data. And finally, I think I sort of touched on it this morning, but I believe that we still have to do a better job of communicating what we do and the importance of what we do to the public, and I see that as a real challenge, maybe not a research challenge, but if we're going to survive as researchers, we have to do a better job of doing that.
Okay, thank you, Clint. So common themes that cut across, despite the disparity of the problems, from the order days prediction to the decades to the millions, billions of years. But there are common themes of multi-scale behavior, linking scales, multi-physics, the need for more resolution, the need for more physics, subgrid scale models, uncertainty quantification, assimilating data, the role that machine learning can play as surrogates to accelerate many of these difficult problems. So there are a lot of commonalities that we've seen. So at this point, let's see how much time is left. But
we're out of time.
we should, okay, well, 6 minutes, okay. So let's open it up to some questions. And maybe we could take a question from someone, okay, back there, a student.
That, big area and directional take in the future is how much, we do these multi-physics, multi-scale models and collaborating. Like, what's the biggest barrier to getting better collaboration? Because it sounds like the future directions requires more domain knowledge being integrated across various different areas and a lot of people collaborating together to kind of solve these more, couple challenges. What is in your guys' viewpoint the biggest challenge to collaboration? How can we, best lower those barriers to solve these, complex problems that cross many domains?
Okay, good question. So anyone want to start?
Well, it often comes down to money and funding, unfortunately. I think the agencies that do fund are trying to get different communities to talk to each other. There's a lot of barriers. I mean, in my community, there's 30 years of history, and then if you go talk to the hydrology community, there's 30 years of history in coding, and so their codes are 30 years old, some of them. Our codes are very mature, some of them. And then you're trying to put, these codes together, and they don't necessarily fit. Maybe they don't even run on, like one of them might run on Windows, and the other one might be on, seriously, and the other one on Unix. Or a part of it might be proprietary. So I think the answer to that question is we do it in baby steps. I mean, we try to just sort of bite off one application at a time, and deal with that, because that's kind of the only way we can make any progress.
I can add to that. Two anecdotes. The one is that the codes that we have developed separately, like the atmosphere and maybe the ocean, we're basically slapping them together, and then now the ice, the cryosphere, land ice comes into the fold, and but now this slap together codes will no longer potentially do some of the really important problems, like the moving boundaries. Like, so as the ice sheet melts, not only so the grounding line retreats, that changes the ocean geometry. No ocean model right now can actually change its boundary geometry. I mean, they're beginning to fiddle around with this now. On top of that, the land, the lithosphere, basically lifts up, so isostatic adjustment. So that boundary is going to move. And then the gravity field from the ice sheet actually produces such a strong gravity field that when it melts, basically the local gravity reduces so far that actually local sea level is going to drop a little bit and the far field rises. Again, no model is able to do that. And to do this well requires basically bold steps to maybe potentially we do this from scratch, and convincing, doing the investments to and the recognition this could potentially be done. Let's try this from scratch. Is very hard. That's one thing. The other thing is just communicating between the computer scientists, the computational scientists, and then the domain scientists can also be hard. The anecdote being between there's been sort of a split where really DOE basically pushed the development of new unstructured mesh modeling capabilities in climate models, right? And so that took quite a while. It's a hard problem, right? And so you want to basically advance this, but then basically the domain scientists were up against the boundary of delivering for the next, let's say, IPCC report, and then suddenly those investments into new generation algorithms, because they don't arrive in time, they get scrapped, or maybe not by doing something new and basically separating. So there's this communication, the willingness to talk to the compiler guy, right? So I'm an oceanographer. Suddenly I'm talking to someone who builds the LLVM compilers. That requires some patience and willingness to basically sit through it and to learn, right? And so that's as simple as that sometimes.
All right, thank you, Patrick. Stella, do you want to take a crack at that?
Yeah, I mean, one of the barriers is inertia, right? We just get set in our ways with our codes. Money helps a lot, I think. That's one axis. But having an institute like Oden is another thing where you can just get people naturally talking at coffee, eating lunch together, and having things like this where you actually learn what other people are doing, and that gives you some basis of which to talk about future collaboration. But it really takes effort to kind of form these centers. They don't just appear, right?
Okay, well, I think that's a great note to end on. Are we at the end of our time? Or should we? We are at the end of our time. So Oden Institute as a mechanism for bringing people together and interacting and cross-fertilizing ideas. I think that's a great way to end the day. We will hear some final remarks from our fearless leader. But let me just say that in 1973, who could have imagined in 1973 when this institute was created that the sorts of complex simulations and data assimilation and predictions and multiple scales that we've seen, who could have imagined that those would be possible, except maybe Tinsley? All right, well, thank you all.
All right, I'm going to use the mic since I know we have people upstairs, and also we are recording. So, first of all, I want to thank all the panelists for this afternoon. I mean, it was a really fantastic set of sessions. I really wish we had more time because there's so many questions I know we all have, and each one of these topics could go on. But it's just been an incredible tour all the way from the mathematics and the algorithms that underlie everything, to the emerging, exciting area of computational medicine, to some of the examples of where computation has really impacted science and engineering. And I should say there are many, many more examples throughout the Institute that weren't even touched on today with, for example, materials being another one. But when Stella puts up the answer to the question of the 10-year vision, end-to-end simulation of the universe, it's like, that's a hard thing to follow. But it's how exciting. So I think it's pretty clear, 50 years is a long time, and I think maybe for many fields, one could say that after 50 years, a field is pretty mature, and ask the question: is it still important to invest in? I would say, and again, this speaks to the vision of Tinsley, and not just Tinsley, but all the faculty and the administrators who supported Tinsley through the years, many of whom are sitting right up here in the front. I can see Leszek, I can see Jim, I can see Bjorn, and I can't see beyond that because I don't have my glasses on, Bob. That not only is the field still relevant, it's maybe more relevant than ever before. And you just got a sense this afternoon from, there is so much to keep us busy. So to the young people here, if you're worried that maybe you made a wrong choice and you would have been better off, say, doing a pure computer science degree, maybe in the short term you could make a little bit more money, but in terms of having a long career of working on problems that really matter to the future of the world, I think you could not have made a better choice. So I think that that's a really good thing to take away. One regret I have about today is that there really hasn't been time to share with, especially those of you who have come from outside, what's going, the now and the future of the Institute priorities. You got a little bit of a sense of it this afternoon. We've really reaffirmed our commitment to high-performance computing. The partnership with TAC is, again, never been more exciting or more important. We, like everybody else, have been thinking very hard about data science, about AI and machine learning. You can't deny that it's revolutionizing the ways in which we use computing, both in traditional areas and in new areas that are coming up. We've been thinking hard. We've made a real priority with computational medicine. Again, as you heard this afternoon, this is the place, and now is the moment to have an incredible impact on how computing changes outcomes for patients and changes the way that medicine is done. That's a really exciting area in the Institute. Computational materials is another area, sort of everything around everything you read in the news about the nation and the need to bring manufacturing capability back, and the role of also materials and all of that. We as an institute have a long history of partnerships. And again, this is something that's a huge priority. So I'm going to say a few things that are directed for those of you who have been here and left and have come back and visited today. We have a number of really strong partnerships, many of which go back decades, some of which are more recent, but we are always looking for more partnerships in education and in research. Our students are amazing. They're amazing when they come here, and then they get put through, for those of you who remember, the grueling Area A, B, and C classes. And so by the time they have come through a couple years of classes, they're even more amazing. And then they're engaged in these interdisciplinary research groups. So if you are out in industry or national labs and you're looking for interns, our students love to go out into the world. We love to have our alumni, our former postdocs come back and give talks. So this is a plea. If you find yourself in Austin or you want to come visit Austin, please reach out to us and come and visit us. We have Oden coffee hours almost every Monday morning at 9:30 up on the 6th floor. If you happen to be in town, come and join us for donuts and kolaches. There's still a crew that have lunch at O's fairly regularly at 11:30. There's a smaller coffee crew that meets in Leszek's office for espresso afterwards. I'm not sure whether Leszek wants a general, but in all seriousness, it's we would love for you guys to stay connected. And then maybe just the last thing I'll mention in terms of an institute priority is the outreach component. It's come up a couple times today. I think never before has there been a more important time to ensure that a commitment to foundational research in math and computing is so essential. And yes, AI and machine learning are the shiny new kids on the block, and they're getting a lot of attention, things like quantum computing, but to ensure that not only is there research funding, but also that there's just a commitment at the university level, and that the next generation of students are making good decisions for the planet about what the education is going to be in. So this is a huge priority for us. We do that through what we do here in the Oden Institute, making sure that we are a really fantastic place for people to be. We're also very focused on helping to contribute to the national pipeline. We have a couple of nascent efforts in engaging with local high schools and even reaching further back into middle schools and grade schools. So again, to those of you who are not here now but are connected to us, if this is something that's of interest to you, we would love to have you engaged. So that's not quite the end of today. You still have a chance to interact more. We have real champagne. One of the privileges of being the director of the, I believe, where's Maria? God, we do have real champagne. Yes, we have real champagne. May not be. One of the privileges of being the director of the Oden Institute is that the staff have learned very quickly that they have to run all menu options by me, especially the wine selection. And so we have posters. The posters are on the ground floor. They're spread throughout the floor. Some of them are in the connector lobby. Some are in the front lobby. Some, I think, are in the corridors. We've got pictures playing in the Viz Lab. I think there's some food still in the Viz Lab. So please mill around. We have posters from almost, not quite all, but almost all of the 25 groups and centers that are represented in the Oden Institute. But if you're a current CSEM student, put your hand up. There's a bunch, so there's a whole slew of them here, so Doug's got his recruiting eyes open. But please, take the time to meet someone you haven't. And then just very lastly, before we move out into the poster, you can imagine the complexity of putting on an event like this. And it has been a huge, huge lift, but you also have just seen the incredible attention to detail, all the little things, like the signs, the people out there in the street, even the beautiful blue, the Oden blue as we call it, shirts. Just so much. It's just been fantastic. And we are so lucky to have an amazing staff. So I think there's a whole lot of blue people back there. I can see the blue. Thank you, guys. All right. And is Anasi's not, where is she? Oh, she's hiding. So there are two people who have pulled a particularly large load, Maria, who has been amazing, and Anasi, who has spearheaded this whole thing. So a huge thank you to both of you, Maria and Anasi. All right, this is wonderful. I feel like, it's just so much fun despite the work. We're not going to wait another 50 years to celebrate everything this institute is. Can't promise we'll be doing this every year, but again, it's so wonderful to see you guys. And I want to give a special shout out to Clint and his group, because I think by far you won the award for the most alumni. How many did you have come back?
I'm not sure. Everybody that was a group member of my group.
Look at that. We should have run a competition. That's good. All right, grab a refreshment and enjoy the posters. And thank you, everybody, for coming.